Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. And today we're looking at lesson 2.9, which again is on static equilibrium. But we're going to take an example and look at it in great detail with this particular lesson. It's a very important concept, this static equilibrium, and so we will take an example and work it completely through step by step. It involves some geometry, some algebra, and some trigonometry. And so there's a lot of steps involved, a lot of detail, and we will go through that completely with this example. So here's a typical example of a static equilibrium type of a problem. We have an object that's suspended by a cable here, and then there are two cables which hold it in place. And so the objective then is we need to determine the tension in the cables. In this case, our object is 15 kilograms, and we're given the angles of these cables here as well. This one being 35 degrees, that one being 73 degrees. And so here we'll call this one T1, we'll call that one T2. And what we need to do is we need to find what the tension forces are for T1 and for T2. And so the way we're going to do that is we'll use balanced forces both in the x and in the y direction, and that will be the way in which we will solve this kind of a problem. So we're looking for the magnitudes then of the forces of T1 and T2. So we'll rework our diagram so that it's a little bit more manageable, and then we can write out our equations a little bit more easily that way. So we'll set up our x and y axes like so. And if you recall, this angle was 35 degrees and this one was 73. So when we redraw the diagram, then using geometry, then this angle then is 35 and that one is 73. So that's just a little bit of a geometry from way back. So here we have T1, there we have T2. And there's our angles. Now what we need to do with these is we need to set up the components both in the x and the y direction for both of them. Now the most common mistake with this is not recognizing that both T1 and T2, they each have a y component and an x component. And the most common mistake is just having one y component for both of them. And that's not going to work. And so you need to recognize, and that's why I usually draw them this way. I have the y components way out here in the wings. That's to remind myself that each one of these has a y component. They both have y components, they both have x components. And that's why I like to draw it this way here. And here we have our force of gravity from our object, our 15 kilogram object. Alright, so now we've got our diagram, we've got our workable here, now we can set up our equations. So we need a balanced force equations both in the x direction and in the y direction. So let's start with the x direction here. So we have one component over here, T1x, and we have another component over here, we have T2x. And so those need to equal each other. So T1x has to equal T2x. So we have T1 cos 35 degrees equals T2 cos 73 degrees. That's as far as we can take that equation for now. We will need to make use of that again later on. However, that's as far as we can take that equation in the x direction for now. So let's move on to the y direction then. So in the y direction, we have the two components again. We have T1y, T2y. And these are going to be T1 sine 35 now, which is this one here. And this one here, this would be T2 sine 73 degrees. And these are both in the up direction, so the sum of these two, T1y plus T2y, has to equal 15g. So there's our second equation there. And now what we're going to have to do is we have two equations, two unknowns, and so the best way to do this is probably with a substitution. So we'll make a substitution there. and we'll go back to our first equation here, and we'll get an expression for T2. T2 from this equation here is going to equal T1 cos 35 divided by cos 73. And then we'll substitute it into the other equation for T2. And that way we'll just have one unknown and we can solve for that unknown. So let's work this through. Let's work this through with the algebra here. So we'll substitute T2 in for that equation over there. So then our equation now looks like this. T1 sine 35 plus T1 cos 35 sine 73 divided by cos 73 has to equal 15g. All right, now what I'm going to do is I'm going to teach you your first trig identity. Yes, this is what's known as a trig identity. You may not have come across it in math yet, so if you haven't, then I am honored to be teaching this to you for the first time. So when you have an expression like this, sine theta over cos theta, that equals tan theta. And I will prove it to you. So if sine theta equals opposite over hypotenuse, okay, that's sine theta, the opposite side over the hypotenuse, and cos theta equals the adjacent side divided by the hypotenuse, well, then sine theta divided by cos theta equals opposite over hypotenuse divided by adjacent over hypotenuse. Now, anytime that you divide by a fraction, you multiply by the reciprocal. So I'll write that down there. So now we're going to multiply by the reciprocal. So we have opposite over hypotenuse times hypotenuse over adjacent, like so. And the h's cancel, the hypotenuses cancel, and you get opposite over adjacent. And what does adjacent equal? It equals tan theta, because tan theta is opposite over adjacent. So sine theta divided by cos theta equals tan theta. And so we can make use of that trig identity to make this equation a little bit simpler. So instead of that, now it's going to look like this. So T1 sine 35 plus T1 cos 35 tan 73, because we have sine 73 divided by cos 73 equals tan 73 equals 147, which is 15 times 9.8. And so now if we just do the arithmetic on there, we get T1 equals 45 newtons. All right, so we've done a substitution, we've used the trig identity, we found T1, and now we can go back and find T2. And the easiest one to use would be this equation right here. And so T2 then is going to equal T1 cos 35 divided by cos 73. And we put in our value for T1, which is 45, which we just found out. And put those numbers in, do the arithmetic, and we get T2 equals 127 newtons. All right, so so now we've got T1 45 newtons, T2 is 127 newtons, and so then we have solved this particular problem with a problem of static equilibrium. So we made use of geometry, algebra, and trigonometry, a trig identity. And the important thing to remember is that the two cables, both of these, they both have y components. Okay, that's the most common error, is not recognizing that these two, they both have y components, and of course they both have x components. And keeping that in mind, then that'll help you avoid the more common error with this kind of a problem.